Welcome back. This is a continuation of the lecture last time about kernel and range of a matrix. So let's recall, if you have an m by n matrix, you think of it as a map from Rn to Rm, and associated to it there are the following subspaces. There's the range of A, and that's just another word for the image of A, and that's also realized as the column space of A. It's the span of the columns of A, and that is a subspace of Rm. Okay, on the other hand, you have the kernel of A, or another word for that is the null space of A, and that's a subspace of Rn. And so remember the definition of these subspaces. The kernel is the set of vectors which get sent to 0 by A. It's the vectors in Rn which go to 0, and the image is the vectors in Rm which you hit by applying A to all of the vectors in Rn. As V runs over Rn, you take all of the vectors AV, that's the subspace of Rm. Okay, so that's where we were last time. Now what I'm going to do is introduce the transpose of A. So since A was m by n, of course the transpose is n by m. And so it goes the other way. If A is a map from Rn to Rm, then A transpose is a map from Rm to Rn. So I'll draw the arrow in that direction. And everything I said about A, I can now apply to A transpose. So let's look at that. So over here, I can take the image of A transpose. It's a subspace of Rn. And what is it? It's the set of vectors of the form A transpose W, where W runs over all of Rm. You apply A transpose to all of those, and you get the bunch of vectors in Rn. That's a subspace of Rn. And similarly, the kernel of A transpose, well, that's a subspace of Rm. Those are the vectors which get taken to 0 by A transpose. So it's just exactly the same definitions as before, with A transpose in place of A. Okay, now note, we have another way of thinking of the image of A transpose. Remember, the image of something, the image of A transpose, is the column space of A transpose. Well, the column space of A transpose is the exact same thing as the row space of A. So this brings the row space of A into the picture. Usually we're just going to think of it as being the column space of A transpose, but there it is. Okay, so let's put this all together. We have a map, a matrix A from Rn to Rm, and we have its transpose going in the opposite direction. And now we have these basic subspaces. There's the kernel of A. There's also the image of A transpose. Those are subspaces of Rn. And the image of A and the kernel of A transpose live over here in Rm. So those are the four fundamental subspaces. And I'll remind you that the image you can think of as the column space. So the image of A is the column space of A, and the image of A transpose is the column space of A transpose, or equivalently the row space of A. Okay, so this is a nice picture. You have these four basic subspaces, and they all fit into this picture. One natural question is, what are the dimensions of these spaces? Do they have some relationship to each other? How does this work? So that's what we're going to look at next, at the size of these spaces. So let's start by doing a very basic example. So this is an extremely simple matrix like this with some ones and zeros. So that is to say, A takes x, y, z to xy. So it's just projection on the xy plane. You just throw away the z coordinate. It's an extremely simple operation. A transpose, of course, is now this matrix. So let's just write down what all of these spaces are. It's a map from A is a map from R3 to R2. And let's see, what do you want to do first? Let's look at the image of A. That's easy enough. The image of A is just the column space of A, and that has two linearly independent vectors in it, 1, 0 and 0, 1. And it's inside R2, so you're getting all of R2. So the image of A is clearly R2. All right, let's see, what next? Let's look at the image of A transpose. Well, that's the column space of A transpose. That has these two linearly independent vectors in it, 1, 0, 0 and 0, 1, 0 in R3. And that they span the xy plane. The image of A transpose is the xy plane. That is to say, it's the vectors of the form xy, 0. The last coordinate is 0. Okay? And in any event, it's two-dimensional. All right. Now, let's see. What next? Let's compute the kernel of A. Okay, well, remember, to compute the kernel, it's a Gaussian elimination thing. Well, this is very easy. Here's A. It takes xyz to xy, and if that's 0, the only way is if x is equal to 0 and y is equal to 0. And this matrix is in row echelon form already. It's easy to see the kernel is the matrices, the vectors 0, 0, z. That's the z-axis. Okay, and over here, what's the kernel of A transpose? Well, let's see. A transpose takes xy to xy 0. I forgot a 0 there, sorry. And the kernel is nothing. The kernel of A transpose is just the 0 vector. So there are your four subspaces. The image, the two images, and the two kernels. And let's write down their dimensions. So the dimension here is 2. And the dimension down here, this is a line, this is one-dimensional. And notice that 2 plus 1 is equal to 3, which is the dimension of the ambient vector space R3. Here, this is two-dimensional. And here, this is zero-dimensional. And 2 plus 0 adds up to 2. And this is an illustration of the general fact. The spaces add up to the dimension of the bigger space. All right, so let's state that as a theorem. Suppose you have an M by N matrix A, which is a map from Rn to Rm. You have its kernel, and you have the image of A transpose. These are both subspaces of Rn. The statement is that the dimensions add up to n. The dimension of the kernel of A plus the dimension of the image of A transpose add up to n. And it's very, very important and helpful to keep in mind that the subspaces that you're adding, the dimensions, they're subspaces of the same space. You're not saying something about adding dimensions of a subspace of Rn and another subspace of Rm. It's entirely in Rn. And similarly, if you apply this to the transpose, of course, by symmetry, just applying the theorem to the transpose, you get the same statement for the transpose. And it's also helpful to keep in mind that there's really just one statement here, and you're applying it twice. There's not sort of two different facts. And this is that the dimension of the kernel of A transpose plus the dimension of A adds up to m, the size of this ambient space over here. Okay, let's look at an example. Let's take, this is going to be very similar to the previous example. Let's take A to be the matrix 1, 2, 1, 1, 1, 1. So this is another 2 by 3 matrix. It's a map from R3 to R2. And let's see, what can we say about it? So let's see, the image is the column space. Well, the columns clearly span all of R2. And it's easy to see that the kernel is 0. And you're getting 2 plus 0 is equal to 2. This is just like before. So, but now let's look at the other side. This is a little different. Now, what's the image? Well, the image is the span of these 3 vectors. Excuse me, 2 vectors, 1, 2, 1, and 1, 1, 1. And, well, they're linearly independent, so that it is what it is. It's 2-dimensional. And what's the kernel of A? Well, now you have to do Gaussian elimination. You apply Gaussian elimination to this, and you get this matrix here, and that's in row echelon form. There's one free variable, which is z, and y is required to be equal to 0. And so you see that this is 1-dimensional. The free variable is z, so the solutions, the kernel, is vectors of the form minus z, z. And that's 1-dimensional. It's the span of minus 1, 0, 1. Okay, so that's good. And again, we'll check that 2 plus 1 is equal to 3. So that confirms the formula from the theorem. All right. Let's do a very elementary example. Let's take A to be the m by n 0 matrix. I think it's always helpful to think of some sort of extreme cases like this to just see what they say. So you have the 0 matrix, excuse me, and A transpose is the 0 matrix going the other way. So both of these maps are the 0 maps, so the kernel of A is what? Well, it's all of Rn. Every vector goes to 0, and what's the image of A transpose? Just the 0 vector. And similarly, the kernel of A transpose is what? All of Rm, and the image is the 0 vector. So you see that sort of illustrates how these vector spaces are of complementary sizes. If the kernel of A is big, the image of A transpose has to be small. And similarly on the other side, this is the extreme case, n plus 0 adds up to n, and m plus 0 is equal to m. Okay, I want to bring the rank into the picture now. So remember, the rank of a matrix A is it's the dimension of the column space. And, well, the column space, of course, is the range. So we conclude that the rank of A is just another way of saying the dimension of the image. So this is an important basic fact. The rank is telling you the dimension of the image of A. Okay. So there are various identities involved in that this introduces. So for example, if you have an m by n matrix and A transpose is n by m, then what do you have? The dimension of the kernel of A transpose plus the dimension of the image of A, what do those add up to? Well, let's see, these are subspaces of Rm, so these add up to m. And, well, the dimension of the image of A is the rank. So we call that R. So this gives you a formula for the dimension of the kernel of A transpose. It's m minus the rank. And that's often handy. Okay. Now, here's an extremely important and non-trivial fact. It's that the rank of A and the rank of A transpose are the same. So rank of A is equal to rank of A transpose. Let's see. Let's think about what that means. So remember, the rank of A is the number of linearly independent rows of A. And so I'm saying that the number of linearly independent rows is the same as the number of linearly independent columns. So let's look. Well, this basically comes down to row echelon form. So let's look at an example. Suppose I had a matrix which was already in row echelon form and it looked like this, and I'm putting stars here to indicate that they don't really matter. Suppose this was your matrix in row echelon form. It has two pivots. So that says it has two linearly independent rows. The rank of this matrix, the number of linearly independent rows is 2, and they're 1 star star and 0 1 star. On the other hand, how many linearly independent columns does it have? Well, also 2, the 2 pivot columns, which are 1 0 0 and star 1 0. And so this last column doesn't matter. It's linearly independent on the previous 2. And so that's one way to think of this identity. It's the number of pivots when you put the matrix in row echelon form. Okay. So that says that of these 4 subspaces we were talking about, if we're just looking at the dimensions, 2 of them have the same dimension. So that cuts down the computations a little bit. So let's draw a picture. You have the kernel of A over here, and you have the image of A transpose, subspaces of Rn, and you have the kernel of A transpose and the image of A. And these 2 bottom ones have the same dimension, which is the rank. So I wrote equals here for the dimension. The dimension of the image, both of those images are equal to the rank, which is to say the rank of A, and which is equal to the rank of A transpose. So that says that this kernel has dimension n minus r, and this kernel has dimension m minus r. So the way I like to think of this is that if you're trying to figure out these subspaces, you have these 2 subspaces of dimension r, and then the complementary subspaces which of dimensions n minus r and m minus r. Okay, there's a little bit of terminology here which is redundant. There's some words that we don't need because they're just different ways of saying things that we already have. So let me get those out there, even though I tend to avoid them. So it's the prefix co is the relevant thing here. The co-range, well, co stands for applying something to the transpose. So that is to say the co-range of A is just the range of A transpose. And the co-kernel of A is the kernel of A transpose. Okay, so again, I don't really need to use these terms because I already have words for these things, and I find it easier to limit the terminology and just use range and kernel, but here you have it. And if you use this terminology, you get the following picture. You have the kernel and the co-kernel like this, and then over here you have the range and the co-range. So here are these 4 subspaces where you just use A. There's no A transpose in this picture. I've labeled everything in terms of A. But again, the co-kernel of A, I prefer to think of that as the kernel of A transpose. And over here, rather than using the range of A, you might as well just think of that, the co-range of A is the range of A transpose. All right, that's all for now.